So hello everyone, welcome back to our channel, and in today's live streaming we are going to be studying and moving on to our digital electronics. Right, so in last lecture, we had studied about combinational circuits, and we have seen what are the different combinational circuits as well. Right, so today we're going to be studying about the sequential circuits. But before moving on to understanding the sequential circuits, let's try solving some previous year questions on combinational circuits. So let's get started with the first question. Yes. So I will put a timer of 1 minute, and I will give you the time to solve this question first, and then we will see the solution together. Right. So just give me a second. I am adding on my 1 minute timer. Right. So here we go. So I guess you can see the timer now. Yes, and yeah, so you have 1 minute. Try solving this question on your own, and we will see it together how to solve it. Yes, do comment the answers in the chat box in the comment section. Okay. So now let's look at the solution of our question. So the question says consider a 2-bit multiplexer shown in the figure. For the output to be XOR C and D, the values of A0, A1, A2 should be dash. Right? So basically it is asking us what would be the input values to get the output as equivalent to XOR of C and D. Right, one second, let me just use my pointer pen. Yeah, okay. So now you can see this is our multiplexer, and very first I will draw the truth table for my multiplexer. Right. So we have our two select lines S1, sorry, S0 and S1, S0 and S1, right? And for us each S0 and S1, we will have an output in terms of I0, I1, I2, I3. So when both the select lines are 0, 0, then the output is I0. When it is 0, 1, then the next combination is 1, 0, and the last combination is 1, 1. So each combination will give us the output as following: I0, I1, I2, and I3. So this is the simple truth table, and from this truth table I can write an equation. Okay, I don't know why is this happening. One second. Okay, I can write the equation as S0 bar S1 bar I0 plus S0 bar into S1 gives me I1 plus S0 S1 bar I2 plus S0 S1 I3. So this is my function equation. This is my equation for the given multiplexer, right? Now in our case, they have replaced the select lines S1 and S0 as C and D, and they have replaced the inputs I1, I2, I3, and I4 or I3 with respect to uh, A0, A1, A2, A3, and so on. So what we do is in the same above formula, what I do is I will replace the value of S1 with C. Let me change the color. I will replace the value of S1 with C, and I will replace the value of I will replace the value of S0 with D and S1 with C. And similarly, I'll replace the input values I0, I1, I2 and I3 respectively with A0, A1, A2 and A3. So the function we'll get a new function where we have replaced all the above values. And now coming to our question, the question is asking us that the output should be XOR of C and D, right? So what is XOR of C and D? So the output function will be XOR of C and D. So this is C XOR D. That is nothing but, what is C XOR D? We have already seen C XOR D is nothing but C bar D plus C D bar, right? So to have the values output C XOR D, the values of A1 should be 1 and A2 should be 1. That means over here this value should be 1 and this value should be 1 and remaining two terms should be 0. That means what is my answer? My answer will be C, where A0 is 0, A1 is 1, A2 is 1 and A3 is 0. So you can see this is the output that it is giving me, and if you compare it to the truth table of XOR gate, it gives me the same output in the truth table, right? So this is a very simple question. Now let's move on to the next question. This is a simple conversion of this decimal number into its equivalent binary. Right? Now this is a very simple question. If you want to solve it, pause the video and solve it. Let's directly get into the solution. So the answer to this is C. Let's see how we have formed the answer. So in here you have a decimal number where this is the whole digit and these are the decimal terms, right? So while converting such numbers, first we convert the whole digit, then we move on to conversion of the decimal numbers, decimal digits. So the what is the binary value of 41? You want to use the 8421 code. Now when you keep on extending the 8421 code, you can add 32 and 16. So we all know this code, right? So 32 plus 8 plus 1 is nothing but 41. So this is the binary number or the binary equivalent of the decimal number 41. Right? Now let's see how did we convert the decimal numbers. So it's a very simple technique. You just go on multiplying it with 2. Right? So this is our binary number, the decimal number. What is it? 0.6875. It is given. Now very first you are going to multiply it with 2, right? After multiplying it with 2, you will get some answer, right? You will keep it as it is. Now after that what you will do is you will take again, consider only the decimal digits over here, and again you will multiply it by 2. So now you have the answer as 0.75. Again you will take only the decimal digits over here, and again multiply by 2, right? Then you continue this process. Since there are 4 digits over here given after decimal place, you will continue this process 4 times, right? After doing this process, you would see that there are some whole numbers in the given answers. So you start writing the decimal numbers from the first to the last. So first we have 1 over here, so we have written 1. Then we have 0 over here, that's why we have written here 0. Then we have 1, so 1, and then again we have 1, so it is 1. Right? So this is the decimal conversion, binary conversion of the decimal number 0.6875. You just go on multiplying and write the numbers from top to bottom. Right? Very simple question. Now let's move on to the next one. Now this is related to a master slave flip-flop. We are going to study flip-flops right now in today's session also. But let's just see what the question is. This is a very simple question which is asking us master slave flip-flop is also called as pulse triggered flip-flop. Right? Okay. Now, let's move on to this. This is a formula that you need to remember. It's a very simple question. It is just asking us what is the resolution of a 6-bit DAC, right? So, this is a formula that you need to remember. So the percentage resolution of an n-bit DAC is nothing but 1 upon 2 raised to n minus 1 into 100%. Right? Over here it is considering a 6-bit. So we replace the value of n as 6 and then we solve this and we get the answer as 1.8, 1.587, which is approximately 1.6. So our answer is C. Right? Now let's move on to the second question. Okay, this is a very interesting one. The expression has been given and it has asked us what is the reduced equation. So over here we are going to use the Boolean expression laws, right? So very first you can see, okay, I will just dive into the solution. Yeah. So there are really two steps to solve this. Very first we are going to use the De Morgan's theorem and we are going to see the involution theorem, right? So this is our equation. So what did we do? Using the De Morgan's theorem, we have split the terms. Right, so these are the equations. Now after splitting these terms, what you can see over here, there is a and b is common in all terms, right? So I have taken a and b as common and I have written the remaining terms in the bracket. The remaining terms are a bar plus b bar, right? Now what I have done is I have multiplied a b into the bracket. I have opened up this bracket, so it what becomes is a b dot a bar plus AB dot B bar. Now we all know that A bar into A equals to 0. Yes, A bar into A equals to 0, right? Similarly, B bar into B will also be equal to 0, right? So you can see over here, this has become 0 and this has become 0. So we are, what are the remaining terms? The remaining terms are nothing but 0 because you're multiplying it into 0. So the remaining terms will be b into 0, right? B into 0 plus a into 0. So we all know b into 0 is nothing but 0, a into 0 is nothing but 0. So our solution is option C, that is 0. So in such a easy and simplified manner, we have we have reduced the equation, right? Now, next question is using, okay, K-maps are used to minimize the number of flip-flops in digital circuits, layout spaces in digital circuits for fabrications, functions of 3, 4, 5, 6 or variables, and D is CPU. Where are K-maps being used? Yes, so this is a question you need to think on. Pause the video and try commenting the question answer. Yes, it's very simple. We use K-maps for simplification or minimizing function variables. So the answer to this question is C. Yes, this is the detailed explanation before implementing the Boolean function in digital circuits. It is simplified. So to simplify the Boolean functions of these variables, we use K-maps. And for large number of variables, we generally use a tabulation method like as Mackenzie's method. Right? Okay. Now let's move on to the next question. Okay, a logic circuit that accepts several data inputs allows only one input of them at a time through to get through the output is called as. This is a very simple question. It is asking us, it is having several inputs, means many inputs. Many inputs. And what is the second term saying? And allows only one of them to get through the output. That means many inputs and a single output. So what is this device? Very easy, multiplexer. Multiplexer is nothing but many to one, right? So this is just a simple question, multiplexer. Right, so this is a detailed explanation and this is the block diagram. We have data inputs and we have a single output which is controlled by the number of select lines, and number of select lines in a multiplexer is determined by the formula of 2 raised to n. Right, so if there are 4 inputs, then we will have 2 select lines, right? We will have 2 select lines, S0 and S1. Right, so this was about the few MCQs from the previous questions that we have tried solving. Now let's deep dive into our next section, which is called as sequential circuits. Right, now sequence means what? Sequence. So if I draw a block diagram over here, it is just something like this. So say if I am having 3 blocks over here and they are connected in a sequence, then what does this mean? That means the input to the present block is dependent upon the past block or the previous block. The input of the present block is dependent upon the output of the previous or the past block, right? So in sequential logic circuit, the output is dependent upon the present inputs as well as the past inputs and outputs, right? Past inputs and outputs. Now sequential circuits, we have two types of sequential circuits. One is called as asynchronous synchronous, and the other one is called as synchronous. Right, we have two types of sequential circuits. Now the name goes it all, right? So what is a synchronous circuit? So change in the input signal that affect the memory elements only upon activation of clock signals. That means the circuit is very much, the working of the circuit is very much dependent upon the clock signal or the activation signal, whereas the change in the input in a asynchronous circuit depends does not depend upon the clock circuit, and they can change the signals at any instant of time, right? Any instant of time. These are the two types of synchronous and asynchronous sequential circuits, right? Now let's look at the very first one, which is also called as a latch. So what is a latch? A latch is nothing but a feedback connection of two NOR gates or two NAND gates, right? And basically a latch can store 1 bit information. So if this is our latch, it will store 1 bit information. It is a 1 bit single bit memory element, right? It has two inputs S and R. It has two inputs S and R, and depending upon the values of S and R, it will give us an output Q, right? So if the value of S is 1, then we can say the latch is in set condition, and when the R bit is on, we can say the latch is in reset condition, right? Now what is a gated latch? Next type is a gated latch. So the name says it is having some kind of a gate. Gate means it is having a control signal, right? So you can read over here, gated latch is a basic latch that includes input gating and a controlled signal. The latch retains its existing state when the control input is equal to 0, right? Its state may be changed when the control signal is 1, right? In our discussion, we refer this control input as the clock. Right, so it is the gated latch. Gate means very similar to our gates that we have in our homes. When the lock is open, anybody can come in, but when the lock is closed, anybody cannot come in. So it is nothing but the zero condition and one condition. When it is zero, that means it will retain its existing state. We cannot make any change. That means nobody can enter the gate. But when the gate value is 1, anybody can enter the gate. Right, now there are two types of gated latches. First is a HR latch and second is a D latch. Right, its second one is a D latch. Right, okay. Now let's first look at the circuit diagram of a gated SR latch. Okay, so basically this is the gated, this is a SR latch, right? This is a HR latch, and this circuit over here is called the gate, is called the gate. So this gate is responsible for enabling or de-enabling the working of the circuit, right? Working of the circuit, right? Now let's move on to seeing the truth table over here. Now when the clock is zero, when the clock is zero, that means there are no changes occurring. Right, now when the clock is given as 1, the inputs S and R will have some effect on to the output state. Right, now when both the inputs are 0, there will obviously be no change, because set term is also 0 and reset terminal is also 0. So therefore there will be no change in the gate. Now when S is 0 and R is 1, that means the circuit will reset, and when we say reset, the output will be 0. Similarly, when S is 1 and R is 0, the output will be set, because S means set condition, right? And in the last state, when both are 1, we say it's a don't care condition or a X condition, when both are set. Right, so this is a very simple timing diagram, which we can see that whenever the clock value over here is 1, whenever the clock value is 1, we can see there is some change in the circuit. That means we can make some change in the circuit. V means the input is making some change in the circuit. Okay, and this is the graphical symbol of the gated SR latch. You can see over here there are 3 inputs. Let me check if I can zoom. No, I cannot. Okay, I'll use my razor. Okay, you can see over here, this is the graphical diagram. You can see there are 3 inputs, S, R and a clock pin. Clock pin means this enabling pin. When it is 0, no changes. But when the clock is on 1, changes in S and R will affect the output. And we are having 2 output states, Q and Q bar. Right, now let's move on to see the next one. Next one is called the D flip flop. Right, so basically what is the function of a D flip flop is, whatever is the input data, it will give the same data in the output. Right, it will give the same data in the output. Now you can see over here there is a graphical symbol. So this is a D latch, means data latch or data flip flop. So if the value of D will be 0, then the value of Q will be also 0. When the value of D is 1, the output also will be 1. Right, so this block is nothing but the D block, and this block is nothing but the gate. Right, okay. So now you can see over here, when the clock pin is 0, there will obviously be no change. We cannot enable or disable. But when the clock pin is 1, there is some change in the output. But this is, since this is a D flip flop, the value of D over here is 0, so the value of output Q is also 0. The value of D is 1, the output of D is 0. Right, okay. Now in here we have two terms or two types of terms. One is the setup time and other one is the hold time. Let's look at the definition. So the minimum time that the input signal must be stable prior to the edge of the clock signal is called as the setup time, right? Whenever the clock signal is applied, there is some change in the output, but before that there is no change. So the minimum time that the input must be stable prior to the edge of the clock signal, this is the edge of the clock signal, so time prior to this is called as the setup time. And second one is the hold time. So the minimum time the input signal must be stable after the edge of the clock signal. After the edge means, see, this is the edge and this is the after of the edge. So after of the edge, the minimum time that the input signal must be stable, this is the whole time after the edge, and this is the setup time, right? These are the two terms you need to understand, right? Now let's move on to the next one. Flip-flops. Flip-flops are nothing but storage elements based on the gated latch principle, right? It can have its output state changed only of the edge of the controlling clock signal, right? I've already told you this. Now let's consider the two types. The very first one is called the edge triggered and the second one is called the master slave flip-flop, right? Now what does this edge triggered mean? Edge trigger means, see, this is the positive edge of the clock signal. One second, let me change the color. This edge is called as the positive edge of the signal, and this edge is called as the negative edge of the signal, right? So you can see over here the flip-flop is affected only by the input values when the active edge of the clock occurs. This is the active edge or the positive edge. So after the active edge has been occurred, only then there is an output that is being generated, right? Now what is a master slave flip-flop? The name says it, master slave. The slave will listen to the master, right? So if the master stage is active during half of the clock cycle and then the stage is active during the other half, the output values of the flip-flop changes on the edge of the clock that activates the transfer of the slave state. So the slave is listening to the master. You can give a like a simple analogy to this. So the input clock is applied to the master and inverted clock is applied to the slave, right? And in a master slave flip flop, the output is changing only when the slave output is changing, right? Because the master is just like a, you can see over here, this is the master, this is the slave. As I already told you that the positive clock or the active clock is given to the master and the inverted clock is given to the slave, right? So what does this mean? What does this mean? When the clock is positive, when the clock is positive, the master will work, and when the clock is negative, the slave will work, right? Okay. So this is nothing but the master slave flip flop. Now this is okay. This is the construction of a master slave D flip flop, right? This is master slave D flip flop. Now you can see over here in this case, J nothing but is acting as D, right? So you can see over here, since the value of J is 0, the output is 0, and the value, when the value of J is 1, the output is 1, right? So it has how many inputs? This is the D input, this is the clock input, then we have this preset input and the clear input. This is nothing but like the set condition and the reset condition, right? Okay. Now let's move on to the next type of sequential circuit, which is called as which are called as resistors, right? Okay. So, okay, what could be resistors? Now, these are registers. Now, when I say registers in real life or in hard copy registers, we have the notebook, we have the books, right? Say, for example, the bill registers, where it stores everything, right? Where it stores everything or it stores the different events. So, say, for example, you are visiting a new society. So at the entrance, there is a visitor's diary. So in the visitor's diary, all the people who are visiting, their names are being registered. right? So in very similar manner, a register would also work. So we can say when a group of flip-flops is used to store a word, group of flip-flops are used to store a word, then we can say it is called as a registers. Now in our case, it does not mean alphabetical word, it is nothing but group of bits, group of bits. So I'll repeat it. When a group of flip-flops is used to store a word means a group of bits, then it is called as a register. And to store n bits, n flip-flops are cascaded in the register, right? So if in a register the binary information can be moved from stage to stage, then this type of register is called as a shift register. That means what? The binary information can be moved from stage to stage. Stage as in this circuit to this circuit, this circuit to this circuit. Now in your this circuit means what? Each flip-flop, right? Now these shift registers can be classified into four types. The very first one is called as serial input, serial output, right? You can see the input given to each circuit is in serial, and it is giving us an output in serial format, right? So this simple shift register is also called as serial input and serial output register. Now next type of register is called as serial input, but there is a parallel output. You can see over here, these are the inputs, in here, these are the inputs in here, and over here we are having the outputs Q0, Q1, Q2 and Q3. So each flip-flop is giving us a serial output, right? So this type is called as a serial input. The input is given is serial, but the output given is serial. Okay, over only here when I consider only this block, right? Now when I consider the whole diagram, this is an example of parallel input, parallel output. Now you can see over here through these circuits there is a parallel input given to each flip-flop, and over here we are having a parallel output. So this is a diagram of parallel input and parallel output when I consider both this. But when I divide this, and if I consider only this part of the block diagram, then this is a serial input, parallel output, right? So these are the different kinds of resistors or that can be used, right? Now for the exam, let me just yeah. For the exam, what you have to remember is these are the different types of resistors that are available. First one is a serial input, serial output. Then we have serial input,